All electrical motors operate on the principle of magnetism. Notice in this illustration, we are showing two magnets. The magnet to the right has been placed on a pivot, allowing the magnet to rotate. Notice the magnetic field radiating from the two magnets. It is this magnetic field which allows motors, coils, or any inductive device to operate. As a child, I am sure that you have played with magnets at one time or another. You noticed that when the like poles were brought close together, the magnets repelled or pushed away from each other. You also learned that when the unlike poles were brought close together, the magnets actually attracted one another. Now notice that when we bring the left magnet close to the right magnet rotates so that the opposite poles are facing one another. This occurred because the like poles repelled one another and the unlike poles attracted one another. Now suppose we had the ability to flip the left magnet at the exact time so as to keep the right magnet rotating on its pivot point. As you can see, by reversing the magnetic poles of the left magnet, we can actually cause the right magnet to spin or rotate on its pivot point. As you will see in a moment, this is a close representation of what takes place inside a motor when the rotor and shaft assembly is turning. However, motors do not use all magnets to turn the rotor assembly. The majority of motors will use coils of wire to produce one or both of the magnetic fields. Some DC motors, however, will use magnets to produce part of the magnetic field required to make the rotor spin. Current flowing through a wire creates a phenomenon called electromagnetism. Basically, when a stream of charged particles, like electrons, are set in motion, a magnetic field will be created around the conductor carrying the charged particles. The lines of magnetic flux created by the current flow through the conductor will occur in directions perpendicular to the motion of the charged particles. This flux field will completely surround the conductor. Notice in this illustration that an AC current is flowing through the conductor. As the magnitude of the voltage increases, so does the magnetic field being produced by the stream of electrons. Also, when the voltage decreases, the magnetic field begins to collapse. Notice that the magnetic flux field not only expands and collapses in conjunction with the strength of the voltage being applied, but it also rotates around the conductor carrying the stream of electrons. The direction of the rotation will be determined by the direction of the current flow through the conductor. The circulating magnetic flux field being illustrated here actually encompasses the entire length of the wire. We are only showing part of this field so you can better understand its operation. Another magnetic phenomenon occurs when the wire is wrapped in a coil configuration. Notice that the individual magnetic flux fields all add together to make one large circulating magnetic field. Also notice that this magnetic field has a north pole and a south pole, much like a permanent magnet. The flux fields flowing from the center of the coil flow toward the north pole, and the flux fields flowing around the outside of the coil flow toward the south pole. As the individual flux fields rotate in unison, the total magnetic field is increased immensely. It is this ability of the flux fields adding together which makes it possible for motors to operate.